Suppose the income, or the random variable x, of college grads are normally distributed with a standard deviation of sigma of 13,000. We gather data on 100 graduates and estimate the sample mean to be 47,000. We want to find the values of A and B such that we can put a confidence interval around the population mean such that the probability it's in that confidence interval is 90%. So one thing to note here is we know the population standard deviation, which is sigma. So we want to be able to calculate the bounds upon the population mean. So what we're really looking at here is we're going to look at a standard normal distribution, and we're going to identify two bounds over here, call this little a and b, and we want to be 90% sure that mu falls within these bounds. Well, if they were 90% sure there, then 5% of our data is going to be over in this range, and 5% of our data is going to be in this range. Well, with that, we can set up the probability that A, or before we set this up, let's go ahead and realize what we have here is we have x bar is going to be distributed normally with our population mean and a variance of sigma squared over n. Well, we can then normalize this, so we don't have to take the integral of a PDF of a normal, to say, well, let's take x bar, let's subtract off our mu, our mean, and divide by the standard deviation, which is the square root of the variance, and this will be distributed normally with a 0, 1. Well, if this is the case, what that tells us is that the probability that A is less than x bar minus mu over square root of sigma squared over n less than B is equal to 0.90. Because that's from the standard normal. Well, I can look at the value for A and B by looking at the table. And again, that table we want 5% on each side of A and B. So I look at the table. I'm looking on the interior for where I find 5%. I keep going. And it looks like 5% happens right about here. So that's equal to 1.64. It's halfway in between 5. So that's going to be both positive and negative are the values for A and B. But that's for the A and B for this statistic. And we want to find where A and B are for mu. So let's go ahead and put those values in. So the probability that negative 1.645 is less than x bar minus mu over square root of sigma squared over n less than positive 1.645, we know that's 90%. And now that we have that, we can then solve this inner part to solve for mu. So let's go and do that right over here. So that's where we're going to get the probability of negative 1.645 times the square root of sigma squared over n is less than x bar minus mu is less than positive 1.645 sigma squared over n equals 0.90. And all we did is we took this, which was down here, and multiplied each side by that. Now, because the square root is always a positive number, we don't have to switch the signs. So now that we got that, the next thing we can do is we can add x bar to each side. So the probability that negative x bar minus 1.645 times the square root of sigma squared over n is less than minus mu is less than 1.645 square root of sigma squared over n minus x bar equals 0.90. Now we have a negative sign here, and so we're going to multiply each side by the negative 1, which is going to flip the signs. So this term is going to come over here because now it's going to be less than, and this term is going to come over here. And so this is where we get the probability that x bar minus 1.645 square root of sigma squared over n is less than mu is less than 1.645 plus, or rather, let's do it right this way so it's consistent. X bar plus 1.645 square root of sigma squared over n equals 0.90. Okay, so this is a trick where we just multiply by -1, and so we flip the signs. So this sign would be this way, which is why we can take this side and bring it over here, and this side and bring it over here. Well, now I have to just plug and chug, is I know what x bar is. That was given in the data, that's 47,000. I know sigma squared, also given in the data, 13,000. And I know n, which is 100. So I can now just plug and chug. So I have the probability of 47,000 minus 1.645 times 13,000 squared over 100 is less than mu is less than 47,000 plus 1.645 times 13,000 squared over 100 equals 0.90. And when I get this, what I find is the probability of 44,868 is less than mu is less than 49,132 is equal to 0.90. So that tells us that we are 90% sure that the true population mean, mu, is between 44,868 and 49,132. And so that's how we can use, with a known population standard deviation, we can calculate a confidence interval with data knowing what our sample mean is, and estimate a confidence interval of where we know that the population mean is located.